We've built up our own data structure. We've worked within the context of another data structure that was predefined. Now we want to talk about manipulating data structures and maintaining them across a certain set of actions within Grasshopper, right? So the geometry type we'll be working with here is going to be curves. And again, curves have a numerical description like surfaces. It's one-dimensional instead of two, and we call it T instead of U or V. So curves are defined generally as a set of connected points. They're one rung up on the geometry ladder from points, and they have more properties than points, such as length, direction, degree, tangency, curvature, etc. And the control object that allows us to manipulate our freeform curves is called a control polygon instead of a control mesh. So here we have a diagram of a curve with the control points that define it. And if we're looking at degree and curvature, right, those two things are related. And if we start manipulating any of our control points based on our degree, a certain portion of the curve will update, and the other part of the curve will be maintained. All right, so that mathematical description has limits. So the curve is defined by a one-dimensional parameter space. We can think of it as starting at 0 and ending at 1. Does not always do that, but that's the easiest one case to think of. All right, so we can move along a curve with a t value to get a relative location along that curve. Right? So because we're going to be maintaining our data structure across a set of operations, right? The kind of case study here is that we've done something that requires us to modify the data structure, and we need to make sure that the logic to the previous part of the file is maintained. So what we're going to do is decompose our paths. So what was A, B, C instead of curly brackets gets turned into a list of letters. Well, in this case, it will be numbers, but our kind of logic here is that will be A, comma, B, comma, C. And we'll also be using a couple of different objects that will allow us to restructure how our data tree is organized, right? If we have a two-dimensional data tree, we can swap the rows and columns so that what was 0AB can become 0BA. And this will take the place of any flattening or also in some cases of grafting that we have to do in this file, so that we can retrieve a specific tree branch within the data structure. So if I wanted to pull out a particular one, right, I could say give me 0, 0, 0, 3, and 0, 4, so that my data structure is changed in that way, and I keep only certain parts. Okay, so before we go into any more of the objects we'll use with data trees, let's go ahead and bounce back over into our Grasshopper application. And what we're going to be doing here is working with manipulating a data tree, right? And the test case is going to be using curves. So what I want to do is first draw a few freeform curves in my viewport. And I want to do this so that my curves are going to be intersecting in some way, right? So hopefully this is of use to you, or you've run into this problem on how to keep things organized whenever we intersect curves and get points. All right, so we have some points. They're all residing on the same plane, so I could even go to top view if I wanted. All right. So the idea here is that we're going to be manipulating our data trees as we work within our file, and we're going to be setting things up so that our data structure is maintained across the different actions that we do. All right, so the first step is let's go ahead and get our curves into Grasshopper. So I'm going to group this object. These are my input curves. And I'm going to right-click and set multiple curves. 1, 2, 3. You can have as many curves as you want here. It's up to you. Just make sure that they're intersecting. Okay, now if we look under the Intersect tab, there are a couple of different options for working with curves. There's curve, and there's multiple curves. All right, now Kind of what I'm imagining I'd be doing here is that I need to get a point at every intersection. I want to find the tangent line, tangent line from this curve going this way, right? And I also want to do that for this curve going this way. And then I want to draw a rectangle using using this as the orientation for my my shape. Right now, when I have one intersection point and two curves to work with, and I have that for each one of these conditions, it starts to get a little bit messy. So what we're going to do is we're going to set up our data structure to be able to work with that and make sure that the coordination between this curve and this point also matches for this curve and this point, and not this curve and the point that would exist over here. All right, so once we have our curves into Grasshopper, what we're going to do is use the curve object. Now you may have seen the curve or multiple curves intersection object. This is okay, but again, it doesn't really give us an output in a way that is as useful as this other option. And in that case, the data structure is just a list. So what we're going to do is we're going to use the same object input for both of these. But what we need to do to ensure that every curve is tested against all the others is graft one of these two inputs. So I'm going to go to the tree tab and grab my graft. All right, so now I'm grafting, and this set of grafted curves will intersect with all the corresponding curves out of B, right? Which is just a list. So now we have a data structure where it's telling us, based on the pairings of all the curves coming in, so 0, 0, and 0 to 2, and 1 to 2, all of those pairings will give us the corresponding points. All right, so let's take a look at this in a panel. Coming out of P, we have sometimes 2 points and sometimes 1 point, depending on the curve pairings. All right, and let's also look at it as a data structure. So if we look at the data tree through the param viewer, we have P giving us 9 branches and this many points. Now, if I look at this curve, right, this curve has 2 intersections. This one has 1, 2, 3, 4. This one has 1, 2, 3. So we're also getting these endpoints, which is something we need to be conscious of. And it seems like we have a lot more points than what we need, right? Well, what we're getting is at this location, we actually have 2 intersection points. From if this is curve 1 and this is curve 2, it's giving us the combination from 1 to 2 and from 2 to 1. All right, so we want that condition, but we don't want the pairing between 1 and 1. All right, so we're going to use the data tree to remove some of those branches so that we're left with only the ones that are useful to us. All right, so the first thing we're going to do is let's get rid of all this overlap between these collection of paths. And remember that that is done through the simplify object. So I'll remove that connection and slide it over. We're going to go to sets, tree, simplify, take the points out, and now we're left with a simple data tree with just 2 levels. All right, so now we can kind of see that this is the pairing. 1 to 0 is good. It gives us 2 intersections. But 1 to 1 is finding the intersection between curve 1 and curve 1. That's not good. Now, intersections in particular are an example of where you're going to need to be really fluent with your data trees and being able to work with them. Because of all the possible combinations that can result from the intersections, the intersection objects create a data structure based on that. So, typically it's fairly complex. Unlike a lot of the other objects, which might grow it in a pretty straightforward way, we have to be really specific with our intersections and the results we get. All right, so we've simplified our data tree. The next step is let's go ahead and take a look at the tree statistics. So we'll grab this object again from the tree tab. And if we have these paths as text, so I'll grab a panel and we'll put the result of P in there. These are actually, curly bracket 0, semicolon 2, curly bracket. That's actually the characters that represent the path. Well, if we have this, all of the A's, and all of the B's separate, it would be pretty easy to be able to compare A to B, and then we could remove all of the ones that have the same index here, right? So we would get rid of 0, 0, 1, 1, and 2, 2. All right, so the way we're going to do that is we're going to take our we're going to use the decompose, which was back here, to take our path and turn it into just the index values that go with it. Okay. So if we take the path and we go to the sets tree, in the third tab, this is where we're going to be spending a lot of time for the remainder of this course. In this portion of the tree tab, we're going to find decompose path. So again, if it takes 0, semicolon 0, we just get 0, 0, 0, 1, and 0, 2. So if we take those two elements, right, which are each path is now on its list. Each path, which was this string of characters, each path is now on a list in its own branch. Now we want what was A, B, we want all the A's on one list and all the B's on another list. So this is where our flip matrix comes in, right? Where we take what was here on each 0 index location and put it on a new branch. So we're going to go back to our tree tab. Let's grab the flip matrix. All right, so now we have, instead of 9 paths of 2, we have 2 paths of 9. And that makes it very easy for us to explode this tree, which takes our input here and puts each path on its own output, right? So now we can look at just the A's or just the B's. All right, so that's explode. And now we can easily compare A to B through our math operators tab if we check for equality. All right, so we're going to compare A to B, and this will give us some true or false values based on whether or not those two numbers are matching, right? So we saw 0, 0, 1, 1, and 2, 2 can all be found using this conditional test. Okay, so we'll see out of the does not equal, true, these are all the ones we want to keep. 0 to 1, 0 to 2, 1 to 0, 1 to 2, etc.